Do you have any idea of where we are?
I have no idea. You check.
This is no use.
Navigation has been a big problem for many centuries.
For many years, people used to use things like the stars to help navigate. But it was really hard because you had to have various instruments and you had to know what you were doing.
All you gotta do is pull out your phone and say, Google, where am I?
And there you go. This is GPS.
Tourists use it. Police uses it. I bet your mom uses it. Everyone uses it. Around the world, millions of people use the Global Positioning System, GPS, to know where they are and where they are going. This satellite-based navigation system has become a tool for everyone and is used by consumers daily in a variety of ways, from in-car navigation to even smartphones. But how did all of this come to existence? The next few minutes of this video will cover the history behind the revolutionary Global Positioning System.
The idea of GPS was originally used for military purposes, with the intention to route guided missiles. U.S. Navy engineers developed a system based on the Doppler effect, used by radars to be able to determine the position of a fixed point very accurately. The idea of GPS was further developed and came to life in 1973 by the U.S. military, who overcame the limitations of previous navigation systems. The system was originally run with 24 satellites and became fully operational by 1994.
In 1996, U.S. President Bill Clinton recognized the importance of the GPS to civilians as well as the military and decided to make the GPS a national asset. Once the system was made publicly available in 2005, it became extremely popular for consumer applications. One of the first companies to take advantage of the technology was Garmin, who started to develop in-car portable navigation systems. Nowadays, GPS navigation is included on smartphones, and the technology has a wide range of uses, from tsunami detection to fitness tracking.
So how does the GPS system work? Well, as the US government describes it, there are three basic components: the space component, control component, and the user component. First, let's talk about the space component. Right now, GPS works on 24 satellites, which is called the GPS constellation. Now, there are a few more just in case one fails or one needs to be serviced, but the government really considers there's only 24. They've been orbited and positioned in a way so that there are 4 satellites orbiting above every point on Earth at any given time. One process I'm going to talk about is called
Trilateration. Seems like a complex word, but it's a pretty simple mathematical concept. Let's see how it works with the Global Positioning System. On the screen, I have a definition from dictionary.com, but it seems a bit confusing at first, so I'll take you through step by step. The Global Positioning System uses 2 basic components: GPS satellites, as shown here, and GPS receivers, which I'll get to on the next slide. Each satellite is launched into space along one of many orbital planes. It usually travels around the globe twice a day, 20,000 kilometers above Earth's surface. Pretty fast, eh? The satellites are equipped with atomic clocks accurate to the nanosecond, as well as broadcasters emitting high-frequency, low-power radio signals to Earth. Here we have a standard GPS receiver. In order to figure out its location on the globe, it needs to know its latitude and longitude. The receiver has a quartz clock inside, able to measure time intervals fairly accurately, down to the millisecond. The receiver knows that the satellite signals travel at the speed of light, so by multiplying the speed of light by the time it takes for a signal to travel through space, the receiver can determine its distance from the satellites. That's represented by the equation that's shown at the bottom of the screen. Now remember this, because it's crucial for the next step. Here is satellite A. The receiver calculates that the signal had a 0.05 second travel time. Using the formula shown previously, it determines that the distance from the satellite is 15,000 kilometers. That should be it, right? Well, there's a noticeable flaw in this diagram. The receiver can be in any direction from the satellite, so the possible locations are infinite, represented by the red circle. Right now, the information on its own, pretty useless. So the receiver listens again, this time from satellite B. It determines that it is 12,000 kilometers away from satellite B, and using the information from satellite A, the receiver has narrowed down the possible coordinates to 2 locations marked with an X. This is where the 2 circles intersect, and the only 2 places where both location distances are true. See where I'm getting at? But it still needs to narrow down to 1 point, so it listens for a 3rd signal. The receiver determines that it is 8,990 kilometers away from satellite C, and this narrows down the location to one single point where all three circles intersect. The problem is, if these measurements are off, the circles still intersect at 3 points. The bottleneck is the receiver's clock, which is only accurate to the millisecond, making the distance calculations inaccurate as well. Here's another example of this. And one more. Right now, the accuracy of GPS is hundreds of meters, represented by the glowing circle, simply not good enough for most applications. I mean, how can a system tell me that I'm on one road, but in fact I'm on the other? It won't work. A simple solution would be to put a more accurate atomic clock in each receiver. Doing that jumps the price up to $100,000 per receiver. Way too expensive for most users. Honestly, I'd rather buy a Tesla Model S than a GPS. But there's another, more complicated and clever solution. If the receiver's measurements are incorrect, a signal from satellite D will not intersect where we originally placed our receiver. So what now? The receiver assumes that its original time measurements are wrong and uses an algorithm to determine its inaccuracy. It then recalculates a time interval for each satellite where all four circles intersect at one point. These time intervals become as accurate as the satellite's atomic clocks without the receiver costing $50,000 to $100,000. Its location accuracy has improved from hundreds of meters to around 1 meter. Now in reality, since we don't live in 2 dimensions, these circles are represented by spheres, but the trilateration process is pretty much the same. Adding in that fourth satellite can even tell the receiver its altitude, crucial for applications such as aviation.
If we were to leave the GPS system as it was, it would actually lose accuracy by 11 kilometers a day. What are the causes for such inaccuracy? I mean, we've got like the most accurate timekeeping devices in all the satellites orbiting the Earth. Where do I even begin? Well, first of all, because the satellites are traveling so fast around the Earth, they undergo something called time dilation, which I'll explain later. And also, the force of gravity that we experience on Earth is not the same as the force of gravity that is exerted on a satellite. That also affects time. Also, we all know that since a few hundred years ago, the tectonic plates shift around. They actually move entire pieces of land. So this also creates inaccuracy in the GPS system. There are many other effects that cause such errors, but they go into such technical detail that they're out of the scope of this video. One of the reasons of the inaccuracy of the satellites is due to something called relativity. Okay, just to briefly explain this, if I am walking on a bus, or if I'm walking 1 meter per second on a bus, then I am walking 1 meters per second relative to the bus. But if the bus is moving 10 meters per second, then I am moving actually 11 meters per second relative to Earth. So essentially what this explains is that velocity is different depending on what frame of reference you're in. Now, one thing that people think is constant throughout the universe is time. 1 second counting here is the same as 1 second being counted on a satellite. But in fact, that's not the case, because time is also relative to your frame of reference. Okay. There are 2 reasons I'm going to talk about in this video on how time is relative to your frame of reference. One reason that causes time to be different between frames of reference is the speed of an object. And the second one is being in a gravitational field. So first let's talk about the speed. So this is described in Einstein's theory of special relativity. And this phenomenon of having different times is called time dilation. Okay. satellites are moving at about 3,900 meters per second. Oh, not squared. Meters per second above and around the Earth. Now, you'll see later on that it doesn't seem significant, but since we need very, very, very accurate times, it will in fact take effect. So Einstein's theory of special relativity for time dilation is expressed as delta Tm equals delta Ts over the square root of 1 minus v squared over c squared. So c squared is the speed of light. Sorry, c is the speed of light, and it's being squared. So that's a very, very, very large number. And you see when you put in 3,900 squared, that's very, very insignificant. Delta Ts is called proper time, and that's basically the time that's measured by the satellite, which is the object that's moving relative to the time being measured, and conveniently noted delta Ts. Delta Tm is the measured time, which is what we see on Earth. So I'll plug the numbers in and see what we get. So delta Tm equals to, or let's say for 1 second actually. For 1 second on the satellite, how much is it in seconds on Earth? So 1 second over square root of 1 minus 3,900 meters per second, and then that's squared, divided by 3.00 times 10 to the 8 meters per second squared. So I actually have to do this not on a regular calculator, but using a calculator on the computer, because the answer is pretty much equal to 1, but it is not. You see, the time measured on Earth is actually 1.000000008 seconds. Now you can pretty much say in a normal scenario that the time on the satellite is pretty much the same time as on Earth. But because when we get down to this nanosecond difference, it takes an effect on the GPS satellites. So this is one way that it becomes inaccurate and has to be calculated for. This is time dilation due to speed. So the second way that satellites become inaccurate and time is different in different frames of reference is because the satellite has is experiencing a different gravitational force than we are on Earth. So this is described in Einstein's theory of general relativity. Okay, relativity. Okay, and this phenomenon having different times based on the strength of the gravitational field that's being exerted on you is called gravitational time dilation. Okay, so again, we're going to be using a pretty similar formula, but we're plugging in a few different numbers. Satellites pretty much orbit about 2.65 times 10 to the 7 meters from the center of the Earth. Not from the surface, but from the center of the Earth, and that's going to be important, and you'll see why. The formula for gravitational time dilation is delta Tm equals delta Ts multiplied by the square root of 1 minus gm over rc squared. So g is the universal gravitational constant, m is going to be the mass of the object that's creating the gravitational field, so that's going to be the mass of the Earth. R is actually the distance that this delta Tm is from the center of that gravitational field, and then c is the speed of light, which is squared. So I'll plug in some numbers again, we'll see what we get. Delta Tm, and again this is for 1 second of the satellite. 1 second multiplied by 1 minus 6.67 times 10 to the negative 11 multiplied by 5.97 times 10 to the 24, extend that square root, divided by 2.65 times 10 to the 7 times 3.00 times 10 to the 8, and then that one squared. So that also equates to a number that is very close to 1, and again I had to use a computer to calculate this. So the time that we measure on Earth for 1 second on the satellite is actually 0.999999992. And again, seconds. Because of this 2 here, when it gets down to the nanosecond, we have to take gravitational time dilation into account. So we saw in the first example that time slows down for the satellite because it's moving fast. And in the second example, we show that time is actually speeding up because it's away from a gravitational field. So both of these factors have to be taken into account when the atomic clocks on the satellites are calibrated so that they match the time on Earth. Okay, so the last error I wanted to explain are the shifting of tectonic plates. So we all know for hundreds of years that tectonic plates usually move back a few centimeters every year. And this does have an effect on the GPS system if you want to get really accurate precision location. So essentially, the GPS satellites used to have an orbital model which they were kept and maintained constantly, and this orbital model was very precise so that they would know exactly where their location is on Earth even though they were on space. But this didn't really work out so well because of the shifting of tectonic plates and other atmospheric and technical errors. So this inspired the creation of the differential GPS system. And essentially what that is there are about 100 base stations around the world that are constantly calibrating the orbital models of these satellites so the satellites always point to the exact same locations every year. Because if not, then one point here would then be 1 point a year later because of the shifting of tectonic plates. So that's basically the last error system. So the last segment that I still have to talk about is the user segment. And the reason it's last is basically all you need to use the GPS system is a GPS receiver.
Just like the internet, GPS is now an essential element of our global infrastructure. GPS receivers are found everywhere from cell phones, watches, and even ATMs. The applications of the system are endless. GPS is used in many sectors including agriculture, aviation, and even finance. It is even used to save lives in search and rescue missions and help emergency service personnel locate victims. Farmers use GPS coordinates and geographical information systems to get precise geotagged soil samples to know where to plant their crops. Airliners and pilots use GPS to navigate along efficient and safe routes. GPS is also even used in financial institutions, not for the location service, but for the extremely accurate timing. They are able to timestamp transactions to within 100 billionth of a second.
Well, that's GPS. It got us from wilderness to civilization.
It's such an amazing and complex system, but it just works. We all hope you learned something.
Thanks for watching the video.